Ever feel like you're trying to understand information that's just locked away, maybe in different digital formats or, from systems you don't fully get?
Yeah, like having puzzle pieces from different boxes. They just don't fit.
Exactly. It's frustrating when you want the full picture. Well, today, we might have found something that could really change that.
We really have. We're doing a deep dive into this new method called Vec2Vec. Now, it sounds technical, I know, but the core idea is actually pretty elegant.
Okay.
It basically lets us translate how AI understands text, these things called embeddings, from one AI system to another. And here's the kicker. Without needing any shared data or even knowing how the original systems work.
Okay, hold on. Text embeddings. Let's break that down first. What are they, and why is it such a headache that different AI models have, incompatible ways of doing them?
Right. So think of embeddings as numerical fingerprints for the meaning of text. AI turns words and sentences into lists of numbers. Texts with similar meanings get similar numbers, mathematically close.
Which is useful for search or categorizing things.
Precisely. Search, recommendations, analysis, all that stuff relies on these embeddings. But the problem is, different AI models, like the paper mentions T5-based GTR and BERT-based GDE as examples, they cook up these numbers in completely different ways, even for the same text.
So it's like they're speaking different mathematical languages, GTREs versus GTEs.
Yes, that's a great way to put it. They represent the same underlying concepts, but the format, the vector space, is just incompatible. You can't directly compare them.
Which makes it really hard to get a unified view if you're getting information from different AI sources.
Exactly. And that leads to this fascinating idea the paper explores, the strong Platonic representation hypothesis.
Platonic. Like the philosopher.
Sort of. The hypothesis is that maybe all these advanced AI text models, underneath their different approaches, are actually learning a common fundamental structure of meaning, like tapping into a universal semantic blueprint.
Interesting. So different languages describing the same world.
Pretty much. And Vec2Vec is designed specifically to find and, translate between these different surface languages by leveraging that presumed common structure.
Okay, so the mission for this deep dive is to figure out how Vec2Vec pulls off this Universal Translation Act, right? Especially when you might not even know the AI that made the original embeddings.
That's the goal. And our source is the research paper that actually introduces Vec2Vec.
So let's dig into that core problem again, the incompatibility. You used the map analogy earlier.
Yeah, imagine two maps of London. One uses miles, grid references starting from, say, Trafalgar Square. The other uses kilometers, maybe a different coordinate system entirely, centered somewhere else.
Both accurate maps of London.
Right, but you can't just lay one on top of the other and have the landmarks line up. The coordinates for Big Ben are totally different on each map. Embeddings from different models are like that same semantic city, different coordinate systems.
Got it. Makes sense why you can't just mix and match them. So how does Vec2Vec bridge this gap without that Rosetta Stone, without seeing examples of the same text embedded by both models? That seems kind of magical.
It feels magical, but it's clever math. The key is that it's unsupervised. That's the breakthrough. It doesn't need those paired examples, text A processed by Model 1 and text A processed by Model 2.
So how does it learn? Where did the idea come from?
Well, the researchers took inspiration from work done in cross-lingual word alignment, figuring out that cat in English means gato in Spanish, for instance, just by looking at how words are used in large amounts of text in each language.
Okay.
And also from unsupervised image translation. You mentioned that earlier.
Right, like turning summer photos into winter photos without seeing the exact same scene in both seasons.
Exactly that kind of idea. Vec2Vec uses techniques like adversarial losses and cycle consistency. The aim is to learn the shared latent representation.
A hidden middle ground language.
Kind of, yeah. A common space where the meaning captured by embeddings from different models can be aligned. Figure 1 in the paper gives a visual intuition. You see scattered points in the original spaces becoming tightly clustered in this latent space.
Okay, cycle consistency. That sounds important. Like checking your work.
It is. It's a crucial self-check. The idea is if you translate an embedding from, say, Model A space into this shared latent space and then translate it back to Model A space.
You should get something really close to what you started with.
Exactly. If you don't, the translation isn't preserving the information. This round-trip consistency, going A to latent to A, or even A to latent to B, then B to latent back to A, forces the model to learn meaningful reversible translations.
Like translating English to French and back to English to see if the meaning survived? Makes sense. And what about vector space preservation, VSP.
Right. VSP is about maintaining relationships. If two documents are semantically close and Model A's understanding their embedding vectors are near each other, then after Vec2Vec translates them into Model B's format, they should still be close.
So it keeps the structure, the relative meanings, intact.
Precisely. It doesn't just translate point by point, it preserves the overall geometry of the meaning space.
Okay, this is starting to click. Let's try that map analogy again to bring it all together. Vec2Vec is translating between these two maps with different coordinate systems.
Right. And it figures out the conversion not by having a list saying Buckingham Palace is at XY on map 1 and A, blah, blah, on map 2 minutes. Instead, it learns the patterns.
How so?
It notices things like, Buckingham Palace is always this far and in this direction relative to Trafalgar Square, and the Houses of Parliament are that far from the palace, and so on. It learns the relative geometry.
It learns the spatial relationships common to both maps, even if the absolute coordinates differ.
You got it. It learns the transformation rules based on those shared underlying relationships between landmarks.
Clever. And figure 2 in the paper shows an architecture. Adapters, a backbone. How does that fit?
Think of the input adapters as prepping the coordinates from each specific map format. The shared backbone is the core engine doing that clever pattern recognition and learning the conversion logic, the shared understanding part.
And the output adapters.
They take the result from the backbone, which is in that common internal format, and translate it back into the specific coordinate system needed for the target map, map B in our example. It's modular.
Okay, neat. So if Vec2Vec is this universal translator, what's the actual proof for that strong Platonic representation hypothesis?
Right.
The idea that all these AIs are learning the same underlying meaning.
Yeah, good question. Figure 4 is key here. It visually shows this. They take embeddings for the same text from different models. Initially, if you measure the similarity between these embeddings directly, it can be pretty low. They look different.
Because they're different languages?
Right. But then they run these embeddings through Vec2Vec into that shared latent space, and boom, the similarity shoots way up. The representations become very, very close in that common space.
So Vec2Vec is effectively revealing that shared structure. It's finding the common ground.
That's the argument, and it's pretty persuasive evidence. It suggests that, yes, these models are converging on some shared understanding of semantics.
Wow. Okay, so the translation seems to work mathematically, aligning these different spaces. But how well does it actually translate the meaning? How did they measure accuracy?
Good point. Alignment isn't enough if the meaning gets lost. They used a few metrics. Cosine similarity, which basically measures the angle between the translated vector and the true target vector closer to 1 is better.
Okay.
Then top 1 accuracy. Is the translated embedding the single closest match to the correct target embedding when compared against a bunch of other possible embedding?
Like a multiple choice question?
Sort of, yeah. And mean rank. If it's not the top 1 match, how far down the list of similar embeddings does the correct one appear, on average? Lower is better here.
Well, what did they find? Did it work well?
Extremely well in many cases. Table 2 shows results for in-distribution translations, basically, translating between models trained on similar kinds of data. They were getting cosine similarities up around 0.9, even 0.92.
That's really close to perfect alignment.
It is. And high top 1 accuracy, too. It means the translated embedding was often almost identical to how the target model would have embedded that text.
Impressive. Did they compare this against anything? Like, what if you just don't translate?
Yes, the naive baseline. They showed that just using the original embedding from Model A and trying to compare it in Model B's space, well, it performs terribly, as you'd expect given the incompatibility.
So Vec2Vec is definitely necessary.
Absolutely. They also had a super strong baseline, this Oracle-aided optimal assignment, which basically assumes you magically know all the right pairings. It's an unrealistic upper bound.
And how did Vec2Vec compare to that?
In some scenarios, Vec2Vec got remarkably close even to that Oracle baseline, which is pretty stunning for an unsupervised method.
Okay, so the translation is mathematically sound. But does it preserve the semantic meaning well enough to be useful? That feels like the million-dollar question.
It really is. And the paper tackles this head-on with 2 types of experiments: zero-shot attribute inference and embedding inversion.
Let's start with attribute inference. What's that?
It means trying to predict characteristics about the original text, like its topic or sentiment or maybe specific entities mentioned, using only the translated embedding. And zero-shot means doing this without having specifically trained a classifier for that task, on the translated embeddings.
You're just seeing if the necessary information is still there in the translated vector.
Exactly. And Table 5 shows that Vec2Vec often did this better than even an ideal zero-shot baseline operating directly in the target space. It suggests the translation actually preserves and maybe even slightly regularizes the semantic information.
Better? How?
Maybe by mapping to that latent space, it smooths out some noise or focuses on the core semantics more effectively. That's just speculation, but the results are strong.
And you mentioned this worked even on weird data like tweets and medical records, stuff it wasn't necessarily trained on.
Yes. Table 3 shows good performance on out-of-distribution data. They tested it on tweets and also on clinical notes from the MIM Keylight dataset. The fact that it could handle highly specialized language, like identifying medical concepts. They mention alveolar periostitis, a dental issue.
Which you probably never saw in training.
Almost certainly not. The fact that it could still translate embeddings related to that concept effectively suggests it's capturing something fundamental about language structure and meaning, not just memorizing patterns from its training data.
That's powerful. Okay, so that preserves meaning for analysis. What about embedding inversion? That sounds potentially worrying, like trying to get the original text back.
Precisely. They took existing techniques designed to try and reconstruct text from its embedding and applied them to the embeddings after they'd been translated by Vec2Vec.
Could they reconstruct anything?
Disturbingly, yes. Figure 5 shows significant information leakage. In some tests using email embeddings, they could recover substantial parts of the original email content in up to 80% of cases, even though they started with embeddings from an unknown source model and translated them first.
Whoa. So you could potentially read someone's emails just from having access to the embeddings, even if you don't know how they were made.
That's the implication. Figure 6 gives concrete examples, extracted names, dates, financial info, someone's lunch order, sensitive stuff, all potentially recoverable from these seemingly abstract numerical vectors, thanks to Vec2Vec's translation capability.
That completely changes how you think about the security of these embeddings. If you work with data from different systems or maybe sensitive data, this is huge.
It really is. The paper explicitly calls out the security implications. Imagine an attacker gets access to a vector database, maybe stolen, maybe leaked. They don't know the model used.
Previously, that might have seemed relatively safe, just numbers.
Right. But with Vec2Vec, the attacker could translate those vectors into a space they do understand, perhaps from a publicly available model, and then apply inversion techniques to try and reconstruct the original sensitive text.
That turns vector databases into a potential liability if not properly secured. It's not just abstract data anymore.
Exactly. The obscurity of the original model is no longer a guaranteed shield. This highlights a potential vulnerability that needs serious consideration.
Okay. A bit scary. Did they look beyond text? You mentioned adaptability earlier.
Yes, briefly. We already mentioned Table 3 showing robustness to different text domains like tweets and medical notes. But Table 4 explored something even more ambitious, translating between text embeddings and CLIP embeddings.
CLIP. That's the model trained on images and text, right?
Yeah.
Multimodal.
That's the one. They tried translating text embeddings to CLIP's space and CLIP embeddings to a text model's space. The results weren't as strong as text-to-text. It's preliminary work.
But the fact that it worked at all.
Exactly. The fact that Vec2Vec could achieve some level of meaningful translation between purely text-based understanding and CIOP's joint image text understanding. Well, it hints at the possibility of using this approach to bridge gaps between different modalities of AI in the future. Very exciting potential there.
Okay, so let's try and wrap this up. Vec2Vec seems like a genuinely significant development.
I think so. It provides a way to translate text embeddings between different AI models without needing any supervision or paired data. It learns this translation by finding a common latent semantic space.
And this provides really strong evidence for that strong Platonic representation hypothesis, the idea that AIs are converging on a universal way to understand meaning.
It certainly points strongly in that direction.
The potential benefits are clear. Accessing information across systems, unifying data from different sources.
Huge potential for interoperability and knowledge sharing. But, as we discussed, there is a flip side.
The security risks. The ability to translate embeddings from unknown sources makes vector databases potentially vulnerable to information extraction and inversion attacks.
It's a capability that cuts both ways, definitely. Something organizations need to be aware of.
This has been fascinating. It really makes you pause and think. If these different AI minds are converging on some universal geometry of meaning, What does that imply long term?
Right. How does that change how we interact with AI, how we trust it, how we secure the knowledge it generates?
Could we eventually have tools that let us query the meaning held in almost any system's data, regardless of its origin? And what new vulnerabilities might that universal understanding expose?
It opens up a whole new set of questions about the future of AI, information access, and data security. Definitely something to keep an eye on.
Absolutely. Lots to mull over there. Thanks for walking us through this complex but really important paper today.
My pleasure. It's exciting stuff.